The last identities we were looking at were our fundamental trig identities that helped us simplify problems and make them easier for us to solve. Today we're going to look at sum and difference identities, which are actually used to help us convert angles we aren't familiar with to angles that we are familiar with. So they're things like, for example, I could have asked you, and I've asked you in the past, to find the sine of 60 degrees. If I asked you to find the sine of 60 degrees, you went over to your unit circle, found 60 degrees, then you said, okay, sine is my y value. My y value at 60 degrees is root 3 over 2, so the sine of 60 degrees is root 3 over 2. But if I asked you to find something like the sine of 15 degrees, you went over to your unit circle, you looked at it and went, uh-oh, the smallest angle on my unit circle is 30. I don't have a 15 degrees on my unit circle. How can I find the sine? Today, you're going to be able to find the sine. So our sum and difference angles, our sum and difference form identities, allow us to find angles that aren't on our unit circle. They allow us to evaluate those angles so that we can continue with the problem if we don't have a calculator. So the first thing we want to do is we want to write down all of our sum and difference identity rules so that we have them to reference. So we have our sum and difference identities. And I will post, just like last time, I'm going to post separate videos in your notes for you to watch on why these identities exist, how they were proved, if you're interested. But just to keep our notes a little bit more efficient in this video, I'm just going to give you the identities in this video, and then you can go and watch the other video I will post in the notes on why all of these identities exist. So the first one says we're going to work with cosine. So we're going to take cosine of A plus or minus B. And this just means we're going to break up something into adding and subtracting two different values that we actually know. So maybe we're going to use 60 and 30, or we're going to use 45 and 90, but we're going to pick cosine values we actually know. We might have to add them, we might have to subtract them. Either way, when we go and do that, then we're going to find the cosine of A times the cosine of B. Now, if you added in the first part, you're going to subtract here. If you subtracted in the first part, you're going to add. And then do the sine of A and the sine of B. And we're going to look at these more, but basically, if you decide to split up your angles by adding them, then this addition sign matches with this minus sign. If you're subtracting your angles, then you're adding on this side. So they go together. Instead of writing them twice, we can just write them as plus or minus, and then minus and plus. Then we also have a rule for sine. So same thing, we're going to have our sine where we can take our A and B and we can add them, or we can subtract them depending on what we need in order to get the angle we're looking for. When we do that, then our formula is going to be to take the sine of A times the cosine of B plus or minus, so the signs match here, sine of B times the cosine of A. So in this situation, when we're dealing with sine, if we had to add them, we're still going to add them. If we had to subtract them, we're still going to subtract them. And then we have a rule for tangent. So tangent of A plus or minus B equals tangent of A, and the signs match here, so plus if we added, minus if we subtracted, tangent of B, all over 1, and the signs don't match here, so minus if we added, plus if we subtracted, tangent of A times tangent of B. And we're going to look at examples of all of these. So we're going to go through and use these formulas so I can show you with numbers what the heck I'm talking about here. And make these make a little bit more sense. So make sure you have those written down because those are the rules we're going to keep coming back to. Those are like the formulas we're going to use and plug into in order to get our answer. And again, if you want to see why these formulas exist, I will post another video in the notes slides for you to watch that'll show you why these formulas actually do exist. All right, so what do we need these for? Well, if we wanted to find, for example, let's evaluate cosine of 75 degrees. Now, cosine of 75 degrees, 75 degrees is not on our unit circle. It's not something that we see on the unit circle. But we do know we can break down 75 degrees to be things that are on our unit circle. So we want to intentionally pick numbers that add or subtract to 75 that exist on the unit circle. So if I want to add to 75, I'm going to use 45 and 30 because 45 and 30 are both on my unit circle and they add to 75. So I can rewrite this. Instead of saying cosine of 75 degrees, I'm going to say cosine of 45 degrees plus 30 degrees, because I haven't changed anything, because 45 plus 30 is still 75. But I've intentionally broken 75 up into two numbers that are on my unit circle. Then I'm just going to use my cosine formula to rewrite this. So now I'm going to say, okay, I have cosine of 45 degrees times cosine of 30 degrees. Since I added to get 75, my formula tells me then I have to subtract here. Sine of 45 degrees and cosine times cosine of 45. Ooh, hello, times sine of 30 degrees. Come back. All right. So now all I have to do is pull up my unit circle, which let me go and copy my unit circle so that we can specifically reference it. Copy. Just in case we don't have it memorized, we can actually look at it and say, okay, the first thing I need to know is the cosine of 45 degrees. So I find 45 degrees, and I know cosine is my x value, so the cosine of 45 degrees is really root 2 over 2. Now I need the cosine of 30 degrees. So I go and find 30 degrees. Cosine is my x value. So my x value at 30 degrees is root 3 over 2. And those things are multiplying. Then I'm subtracting sine of 45 degrees. 45 degrees is right here, and the sine is the y value, so that's root 2 over 2 again. And my sine of 30 degrees is my y value at 30 degrees, which is 1/2. So after I split my number up into two things that I can add or subtract from my unit circle, then I plug those numbers straight into the formula for my identity. And then I go and I look at my unit circle, or I use my knowledge of my unit circle to actually evaluate every piece of that. So I say, okay, cosine of 45 degrees, and I pull out those numbers. And now I'm just going to simplify this as much as I possibly can. So the first part, I'm going to do root 2 times root 3, and because they're both square roots, I can actually multiply them together. When I multiply them together, I get root 6 over 2 times 2 is 4 minus root 2 times 1 is root 2 over 2 times 2 is 4. And then since my denominators are the same, I can combine these to make it root 6 minus root 2 all over 4 to be my final answer. I can't simplify that any farther because I can't subtract square roots unless they're exactly the same square root. And I can't factor a 2 out there because I can't simplify those square roots. That 6 and that 2 are stuck inside the square roots, so there's nothing else I can do there. That's my final answer. So without having a calculator, I was actually able to find the cosine of 75 degrees by using my sum and difference trig identities. So let's try another one. Let's try, for example, let's evaluate the sine of pi over 12. So now, pi over 12, we don't know. It's not on our unit circle. But I can rewrite pi over 12 to be the sine, come on, pen, of 3 pi over 12 minus 2 pi over 12, which you're probably saying to me, why in the world would you do that? And I did that intentionally because 3 pi over 12 is the same thing as pi over 4. If I simplified it, if I divided both those by 3, I'd get pi over 4 minus 2 pi over 12 is the same thing as pi over 6. And pi over 4 and pi over 6 are on my unit circle. So I want to, when dealing with radians, I need to come up with fractions, equivalent fractions that subtract to the one they're giving me, but also reduce to be numbers that are actually on my unit circle. So there might take a little bit of guessing and checking here if you're not too comfortable with equivalent fractions, but you're looking for two fractions that when you subtract them, they come out to give you what you're looking for. You can also, if you were looking at your unit circle, let's see, copy. If I brought my unit circle down here, paste, I don't want all this highlighting. Since I know that I want pi over 12 in my sine value, I could go in and convert my first quadrant. I could say, okay, pi over 6 is really 2 pi over 12. Pi over 4 is really 3 pi over 12. And pi over 3 is really 4 pi over 12. Pi over 2 would be 6 pi over 12. I could go in and convert my first quadrant and then see if I could add or subtract those in order to get pi over 12. So I see if I want pi over 12, I want to take 3 pi minus 2 pi, gives me 1 pi. Since they're fractions and I'm subtracting them, the denominator stays the same. And then I would go in and then simplify 3 pi over 12 and 2 pi over 12 to be pi over 4 and pi over 6. Once I get to this step, then I'm just using my trig identity in order to rewrite it. So now I'm saying my sine rule says I take sine of pi over 4 times cosine of pi over 6. Since I subtracted them, it still wants me to subtract them. Sine of pi over 6 times cosine of pi over 4. And then again, I go into my unit circle and I evaluate each one of these. So I go in and I say, okay, sine of pi over 4. Pi over 4 is right here. Sine is my y value. So root 2 over 2. Cosine of pi over 6. Here's pi over 6. Cosine is my x value. So root 3 over 2. Bring down my subtraction sign. Look for sine of pi over 6. Here's my pi over 6. Sine is my y value. So 1/2. And then cosine of pi over 4. Pi over 4 is right here. Cosine is my x value. So root 2 over 2. And then I just go through and I simplify. When I simplify, I get root 6 over 4. Because remember, when you're multiplying fractions, you just multiply straight across. 1 times root 2 is root 2. 2 times 2 is 4. And again, I get root 6 minus root 2 all over 4, which I cannot simplify. That's not always going to be my answer, but like we've seen with the unit circle, a lot of times we get repeating numbers and repeating answers. So let's also go and look at one that has tangent in it. Let's see. Let's find the tangent of 15 degrees. Tangent of 15 degrees. So we need to think of what can we use to get 15 degrees from our unit circle. What can we add together to get 15? Nothing, because 30 and 0 are our smallest numbers on our unit circle, and 30 plus 0 is not going to give us 15. So we're going to have to subtract. So we want to think, what can we subtract to get 15 degrees? And we could rewrite this as tangent of 45 minus 30. And I got that. I just look at my first quadrant of my unit circle and I pick numbers out that are on my unit circle and I subtracted them to see when I could get 15. I could also use 60 and 45, right? Because those would subtract to be 15. But I'm going to use 45 and 30. There's no other reason than I came up with 45 and 30 before I came up with 60 and 45. So you could use 60 and 45, but I'm going to use 45 and 30. So then I'm going to go in and I'm going to rewrite this using my identity. So my identity says on top to take tangent of 45 degrees, keep the same sign, and then take tangent of 30 degrees. On the bottom, I have 1 with the opposite sign plus tangent of 45 degrees times tangent of 30 degrees. And now I just need to go in and evaluate all of these things. So the first thing I'm going to do off to the side is I want to find tangent of 45 degrees and I want to find tangent of 30 degrees. I want to get those numbers and then I'm going to go back into my original problem and plug in. So my tangent of 45 degrees, my y value at 45 is root 2 over 2. My x value is root 2 over 2. So my tangent of 45 degrees is just 1, because when my numerator and my denominator are the same, my fraction simplifies to 1. Now, my tangent at 30 degrees, my y value at 30 degrees is 1/2. My x value is root 3 over 2. So I'm going to need to simplify this. It's going to become 1/2, change the sign, flip the bottom fraction, cancel my 2's. I get 1 over root 3. I know that I can't leave a square root in the denominator, so I'm going to take 1 over root 3 and I'm going to rationalize it by multiplying the top and the bottom by root 3, which gives me root 3 over 3. So now anytime I have tangent of 45 degrees in my formula, I'm going to replace it with a 1. Anytime I have tangent of 30 degrees in my formula, I'm going to replace it with a root 3 over 3. So I just go back to my formula and my tangent of 45 becomes 1 minus my tangent of 30 is root 3 over 3 all over 1 plus tangent of 45 degrees is 1. And tangent of 30 degrees is root 3 over 3. I can simplify this a little bit because 1 times anything stays the same. So really, the most simplified version of my answer here, I'm going to leave it as 1 minus root 3 over 3 all over 1 plus root 3 over 3. Because I have an answer. It's not that pretty, but it is an answer, and it's pretty simplified. So I am done.